So today I want to introduce one of maybe you are not familiar this one, but now this is a great potential, and probably next couple of years some of a new type of insecticide on the market. That is, I expect. So today I want to just briefly introduce the RNAi, which is RNA Interference, what I've done, what I'm doing now. So before introduced the RNAi, I wanted to hear and thought of this nice insecticide. I would say this is our hero in here to protect the insect pest for agriculture crop and also other medical insect pests. A lot of it. But some of here insecticides already retired, but some of still currently very active. Unfortunately, this insecticide is too strong. It's very strong to make some side effect for some of human toxicity, other non-target insects. So still we're looking for new insight of pest management. Okay, this is not my eyeball. I pick my eye doctor. So, what is RNAi? It is a totally different type of a new mode of action of insecticide. One of the advantages is this is a very target specific, which is protect non-target insects. That is the most advantage of RNAi insecticide, also non-toxic. Actually, you die every day, every single day you eat a lot of RNA in your ingestion. Once RNA ingestion, they destroy it very quickly. But one of the challenging part is RNAi insecticide. We have to screening part. Which gene is the most good candidate? Theoretically, RNAi candidate is 20,000 of candidates from each insect pest. So screening part is most of the challenging. Also, in some of the gene is very critical, some of the gene is not critical. Like your house. Structure of your house, one of part is very important. We take out, your house is crap. But some other part is take out, no problem. And here is RNAi mode of action. In this one, all of protein, no exception. Every protein is come from DNA tube through messenger RNA. Protein is produced. So messenger RNA copy based on DNA, genomic DNA, which is we stage transcription stage, and then protein made by copy of messenger RNA, which is a translation part. So this expression, this pathway, we say gene expression. So RNAi is destroyed to messenger RNA, block this pathway, now protein produced. That is a basic RNAi mechanism. So this is RNA, most of the natural form of RNA is a single strand RNA. But RNAi approach is, RNAi material is a double strand RNA. So once this double strand RNA is insecticide. Okay? This is insecticide. So double strand RNA introduced in the cell, insect target cell, double strand RNA, once get inside the cell, the one of enzyme is dicer enzyme, they chop up. Little bit longer double strand RNA, they chop up, make 21 or 25 nucleotide small siRNA. So this siRNA binding to another enzyme, and then this one binding to messenger RNA, which is the target messenger RNA. We destroy to messenger RNA, and then here, messenger RNA destroyed. So once messenger RNA destroyed, no protein. That is why killing insect. So this is a simple mechanism of RNAi pathway. So what is the RNA application part? So key factor is number one, as I said, which gene is the target gene, which system is the target part. This is the number one issue. It's very important. Number two, how much impact. Some of the gene we block, maybe insect is die. Some of the maybe insect just sick, not die. So that is depend on target gene. Is impact is high impact, low impact. And then number three, second part is how this RNA delivered to target insects. There are many different ways, maybe transgenic, maybe non-transgenic, or very, very different. And last part is RNAi material is relatively expensive. It's very expensive in the 5 years ago. 1 milligram maybe a couple $1,000. 2 milligram, 1 gram, lot. But RNAi actually used only microgram level for each individual insect or 10 insect. But now its cost is decrease, so decrease. So anyway, still this is a cost effective, is one of the factor of RNAi application part. So and how once we selected or we looking for one of the candidate gene, we design to DS doubles the RNA. Important part, we need to avoid the non-target insects. So if we found in the selected nice target gene, but that is overlap to other non-target or beneficial insect, it is not practical. And then we making to this RNA material, and also next stage is how much the application part, dosage, chemical insecticide, maybe ppm, something like that. And how long this impact to persistence. Most of our dsRNA impact is 72 hours, or sometimes 96 hours. After that, this is destroyed, gone. And last one is depend on insect pest, adult stage or larval stage. Maybe Sphaeroid Drosophila, we can both stage, larval stage or adult stage, both. But Caterpillar or Lepidoptera case, we only maybe target the larval stage. So depend on species, depend on target, depend on stage. And here is a target gene. Maybe you're not familiar, housekeeping gene. This is an essential gene of in the all of your cell or insect cell structure. And I'm also interested part in the neuropeptide hormone and receptor part. Most of the case, the dsRNA, the length is between 200 and 400 base pair. Once they get in, they break down 21 and 25. You can figure out how many fragments come out, right? So 100 base pair, if it's 25, 4 fragments come out. 200 base pair, probably 8 fragments come out. And then we have to bioassay parts. Injection and feeding, spray, RNA delivery, and I said earlier, the transgenic, non-transgenic, spray, injection, or base station, whatever. depends on target, depends on different approach. So I wanted to introduce what I've done before, what RNAi approach to one of my target insect, the gene, pheromone biosynthesis activated neuropeptide, which is PBEN gene, and design different Lepidoptera. I tried the Lepidoptera, Hymenoptera, Diptera. So I want to skip at this one, the T7 promoter, using this one and synthesize about 200, 400 base pair of this gene. Okay? And then try to, once we design RNAi is one of the tricky part is big insect, no problem. Caterpillar, moths, I can inject manually and micro syringe, it doesn't matter. But if we Drosophila, small tiny insect, mosquito, and or here is invasive ant like fire ant, we need under microscope and we need a nano injector. Use nano injectors only 1 microliter is a lot, full lot. If it's injected 1 microliter, they burst out. So usually between 20 to 50 nanoliter. So 1 nanoliter is million 10 to minus 6 milliliter. It's a very tiny amount. It's a very tiny amount. If you injection 50 nanoliter, the abdomen is bigger, bigger, bigger. So 1 microliter injection, they burst out. No, we cannot do that. So this is kind of a small insect, is a tricky part. And here is one of what I've done, and with the fire ant, I injected 2 dsRNA. Here is a control, here is RNA, and adult mortality is more than 80% is we got. And then also we inject in the pupal stage. Also here is the RNAi control. Here is relatively not, but also here is the die. But adult part is 80% is we got some result, which is good. So this is injection part. So but injection is not practical. Where is injection? This is no. But once we have injection, why we need injection? So you go to a hospital or visit the doctor office. Most of the cases, doctor prescriptions your medication. But sometimes very serious, what to do? Injection. Because injection is directly to your material, the RNA material circulate in your blood system and then go to target immediately. So once we screen in RNAi and then injection, if with no impact or very less impact, forget about it. We not go to next stage. That is why first we try the injection first, and then if we get high impact, and then we go to next stage is a feeding or other way. So then we try to mortality of fire ant, larvae. Maybe you're not familiar. Ants is larvae. They cannot eating themselves. They always adult give to how to adult is feeding to sucrose containing RNAi material, go back to home, regurgitate, and then give it to baby. Okay? So we monitoring the larval mortality. In the larval mortality with RNAi, we found the baby, which is a larvae, is die. What it means is that is RNAi material from adult to baby. Okay? Does that make sense? So that is which. So next one is I'm going to some of a crop test. So we first try to corn earworm injection. This dsRNA is corn earworm specific RNA. Previous one is fire ant specific dsRNA. Okay, don't confuse that. So that is with injection. Then we here RNAi treatment is nice mortality. Here is a phenotype of a deep form of from the RNAi treatment. Then, okay, here's the exciting. So next, let's try to 3 different crop tests, including corn earworm, tobacco bollworm, beet armyworm. And this is a lot of work. Once we synthesize dsRNA specific and depend on different species, different dsRNA, and then mix the artificial diet, okay, mix the artificial diet and they give it to larvae, and we monitor to larval mortality and pupal mortality or what happened. So here's a case of one of a corn earworm. This is a 0.1 microgram. This is 1 microgram. It's 10 microgram actually is cup. 1 cup in diet containing to 1 microgram, 0.1 microgram dsRNA, and then give it to insect. They feed and then we monitor the mortality. They are significantly different here, controlled as the RNA treatment. That is come from corn earworm. So next, this one is how the happening the larval stage they die, and also deform the pupae, which is via phenotype of RNA treatment. Then the other case is the tobacco bollworm case here in the same, very similar result from RNA treatment, but you can see here the phenotype is different from RNA treatment. All right? And then here's another interesting part. This gene is multifunction. This target gene is multiple. Maybe you remember PBAN is a pheromone biosynthetic activating neuropeptide. This is control in the larval development. Also, this is control of sex pheromone production part. So, if we dsRNA injected to adults, what happened? They do not produce or less production of a sex pheromone. So if less produce sex pheromone, what happens? They cannot make sure the mating chances decrease, cannot make the next generation, right? That is another tricky part, an interesting part of a dsRNA we found. This is RNA. 5 minutes? Okay. If 5 minutes, I will skip at the tube. This video part. So this is a trail pheromone. You know, it's ant is always they follow the once one guy is found in the food and then go back. If it's small tiny one, they take it back home. But as a big cannot take. They go back home and then okay. In the recruit in the colony, go to 3 ants go there. Oh, it's still too big. 3 go back. And then more come back and forth back as a big trail. That trail is not just a random trail. Ant is going back on the day already put the trail pheromone in there. So our strategy is if we block trail pheromone, what happens? They cannot find the food. That is one of our strategies to controlling the fire ant. So last until coming in Covalis, we work in 9 different species from different group of insects with the RNA treatment. We have a number of publications and patents, and also we have done some commercial entity. So that is my story of RNA part. So here's I will just last month in the January, one of a newspaper, not newspaper, science news, one of a magazine, Choi. Here's you see. Ag-bio giant Monsanto developed advanced in the RNAi product is the first RNA product we expect in the 2017 on market. This RNAi only target the corn root worm. So you know, Monsanto is a big, biological and agriculture company and a more transgenic company. They have very strong background of BT, and probably this gene is RNAi in the core expression is the BT to target corn rootworm. So this is the problem I expected. Number one, the first RNAi products, but later then probably a lot of RNAi products depend on target insect. So what is my next job is here actually I come from Florida. In the Corvallis, my job is one of my mission, I developed RNAi too. In here, this different small fruit and nursery pest is here. What I'm doing now in the number one, in the focusing spore wing Drosophila with screening of a lot of screening RNA target genes from this guy. It's not easy, and it's a lot of time consuming and tedious molecular biology work and DNA work, bench work, and the other part is I'm interested part how mass production of RNAi material in some of our different biological systems. That is one of the interesting part. The other part is probably most of you here, you don't like it, the transgenic, I know that. And we develop how non-transgenic deliver to this material for spore wing Drosophila. So I need more research, more funding. Thank you.
I'm sure we all really understand this well. Let's start getting into it. Go ahead.
Two questions actually. Yes. Is there a possibility for identifying a mechanism which would be, would apply to a group of pests? So
yes.
Not actually a specific insect,
yes.
but in a group you could target multiple.
Yes.
And then also could the technology be used to treat other problems, funguses, viruses, everything has RNA as I understand it. Could you actually use this and say, okay, we're going to go after this fungus or this virus and interfere with its?
It potentially is possible, and I'm entomologist, I don't know is how the mechanism of fungus or the part. But first RNAi in the non-product is the one of focusing to bromide in the honeybee. Actually, mite is not insect, but honeybee in the mite bromide. So, in actually the nematode is possible, control nematode with RNAi. I'm not sure virus. I'm not virus person, and so it could be, yeah.
Other question?
Yes.
So the delivery mechanism is based on ingestion or contact. Let's say, for example, Drosophila.
Drosophila, I will try to in the two ways. First one, ingestion. The other way I'm thinking about in the now we are already one of the USDA first in the Florida to control psyllid in citrus. You know the psyllid, green disease and psyllid. Psyllid is one of our vectors in green disease. What they're doing now in water, one of the container water in containing the dsRNA, and then put into plant. Plant in soaking the water, RNA is circulate inside the inside the plant. So psyllid penetrated in the plant, RNA getting to inside. That is not transgenic. It's not transgenic. And because once the water is gone, water is actually containing the RNA is gone, no circulation. That is maybe another way to blueberry part. So RNA delivery is depends on target pest, or it's very different. For example, it's what is good and maybe base system. We get RNA material with put into attractants with together. That is a possibility.
Good question. I was wondering if you know who the regulatory agency will be. If you come up with something great and useful, what are the potential barriers or obstacles that you might see moving it forward?
Yes, regulatory system. Yeah, that is important part. Of course, the EPA is very friendly to RNA material. So I would say it's a very different to chemical insecticide. So,
But there are none registered at the moment.
not at this moment, and maybe 100 already. Yeah. Yeah, that is it.
I mean, I bring it up because one of the barriers we had, for even just getting pesticide credits for this meeting, your talk, there were some questions about it because it's so new. And I think just moving forward and getting the word out that this is a potential viable option. It'll take a little bit of time.
Go ahead, Jason.
Well, I guess kind of a twist on that. I mean, I guess public perception of something like this, people are going to jump to like transgenics and how you're manipulating like an animal species or something like that. Like, do you see any issues coming up with that at all, especially when you have larger ag bio giants like Monsanto doing a lot of research into this, kind of social perceptions can be led to believe one thing even if it's not right.
Social perception?
Yeah, so like, the public, like public, yeah, exactly.
We need more insecticide
Yeah.
other than so that's science part. And yeah, so
If I could comment.
one of my personal, actually 5 years ago, or 6 years ago when I started this project, I doubt. I really doubt. 10 years ago, I'm insect molecular biologist, physiologist. And RNAi is actually the early of 2000, very popular to fundamental questions for other basic science. And then now applied to this RNAi is not actually developed, not first to agriculture part. That is developed human drug. Much pharmaceutical company and the human medical side here, advanced here. Now our agriculture are here. So that technology modified to in the years, and then we developed insecticide. And 5 years ago, I also very doubt, is it really possible to insecticide? But now it's almost there, one of them. That's very surprised. Yes, I know it's probably conception and it's being more technical science.
No, I was just going to say, once products do start coming out, I think that will be addressed because I think a lot of homeowners are going to be the first market for a lot of this. And it'll be labeled as a non-toxic basic approach to this. It's really exciting.
Yes, it's a totally new type of insecticide.
Thank you.